So scaling streaming systems, this is quite a complex topic. So I've been working with a friend of mine from California. I'm from St. Louis, Missouri, by the way. His name's Ning Wang. I met him while he was a contributor on a streaming framework or system called Apache Heron. He was working at Twitter. He was one of the core contributors. Him and I met. We got to talking through open source, and we ended up both becoming Apache committers on the project. And we stayed in touch over the years, and we were approached by a company called Manning Publications. They asked us to talk about, to write a book about streaming. I think one of the more interesting parts of streaming is how do you scale those out, and how do you scale out a streaming job that's moving data in real time? Because you can't stop it. I mean, you can, but it kind of defeats the purpose of, how do you process that data quickly? So why? If everything's in real time, why do we need to scale a streaming system? Well, there is, no matter what framework you're using, no matter what tool you're using, no matter what type of technology, it's always bound by the compute resources in which it runs on, right? So CPU, memory, and so forth. So eventually your computer runs out of resources and you need to scale it. You need to add more nodes to process more data. And this is quite frequent with real-time systems. They come up and they have, say, 5 components, and then Christmas comes by and it has to scale out to 15 instantly. So it's a very known thing and a very common thing in the streaming world, and you have to be able to react to that dynamically to make sure you can process this data in real time or controversial near real time. So to catch you up, we're in chapter 4. We have 2 characters. All the code I'm going to show you, you can download right now. You can get it here on the source code download link. You can catch it here at manny.com, books.Grokking Streaming Systems. And you can, hopefully, if you find this interesting, you can come check it out and, kind of dive into the code. We have Tim and Tracy. Tim is the business owner with a bunch of money, really doesn't know anything about anything. He just likes to solve problems, or he finds a problem interesting. And he's like, hey, let's do this. And then he's got Tracy. Tracy's his lead engineer. Tracy is, typically the one that saves his butt, kind of keeps him on tracks, and usually saves the day. So in the first chapter, we went over the very basic hello world streaming job, where we talked about counting the cars that go through a bridge using IoT sensors. So in the story, everybody figured out that, so basically Tim was too cheap to pay people to sit at the toll booth. So he paid for this IoT sensor job to be built, and, go ahead and emit data from the car, so we knew how to bill, how to keep track of cars, and so forth. And because of this, people were able to get through his bridge so quick that everybody wanted to drive through Tim's bridge. So he had to scale out his bridge, and because of that, he had to add a new lane. And because of adding a new lane, he had to add a new sensor. So he's got 1 sensor up here, pardon the resolution on the graphic, and now we got 2 sensors down here. And because of this, we've doubled the amount of events that the stream job is processing, and we have to find a way to scale it out. Just, to kind of touch in, we had 1 sensor before, we had 1 car lane. Now we got 2 car lanes with 2 sensors, and, cars are just flying through this bridge. Nobody's got to stop. There's no toll booths. The sensor picks up the car and it just knows what to do. Technology is great. So our original job, which I'll kind of step us through here in a minute, we had a DAG, right? So we had a source and we had a operator. Our source was our IoT sensor reader, and then our operator was our vehicle counter. We had 1 of each, right? So 1 per lane. We had 1 sensor per lane, 1 counter per lane, and it worked. When we added 2, things started to gunk up and it didn't work correctly, so we had to find a way to scale out the job. And ultimately what we did is we added 2 sensors, and then we added 2 counters. So we added 2 sources and then 2 operators. And because of this, you have to know, so from here to here, it's easy, right? So this component pushes data to this one, or this component pulls data from this one. Here, you have a little bit more complexity, and you have to understand and know when a vehicle counter will, when one of these instances of a vehicle counter will get data from which upstream component or data source, and how, and how do you predictably route data to that. To kind of get into, before we jump into this a little bit, there's a word we should talk about, and that's parallelization. It's it's a word I can't hardly ever usually say, but it's a word that comes up quite often in streaming systems. It's about scaling out the same thing, scaling out an operation that does the same thing. So if you think about the job that we had before, we had a single component that was pulling events off of a queue, right? So the traffic event would come in, the data source would, the data source would pull the event in, and they would push it on a queue, and then the next downstream component, which would be the vehicle counter, would then pull it off. So there's this intermediate queue that allows for the processing of data, right? And by parallelizing the counter, we're able to pull twice as many events off in the same amount of time as we could when we only had one. And because of this allows us to scale our job out better. And there's a couple different types of parallelism. I'll kind of go academic for a minute. Hopefully, I don't get you sleeping too much. But if you think about a queue of 100 elements, right, and you have one component, imagine there's only one of these. You'd have to do 100. You would have to, and so let's say the operation takes 1 second. If you processed each one of those sequentially, it would take you ultimately 100 seconds to do all of those elements. That's really slow. If you parallelize out that operation, say you scale it out to 100 operators, you can do all of those 100 operations within 1 second. And because you parallelize the component, you're doing the same operation just on a different piece of the whole amount of data, allowing you to process data faster and move on to your scaling systems. And then this brings up another fancy word that kind of came up, another $5 word, as I call it, as we were writing the book, and that's data execution independence. And that's a requirement of parallelism, or parallelizing a component. And what that means is that no operation that's done to an element can be one block or one square on this little array of values, will affect the output of another one. In this top queue here, if we took each one of these number ones sequentially and multiplied them by 4, they would all have the same result, right? In the same fashion, if we took them all at the same time and multiplied them by 4, they would still have the same result. They wouldn't affect one another. And because of this data execution independence, we have the ability to parallelize out our components. And there's another type of parallelism, and that's task parallelism. It's a little bit different, just a little context. Everything's going at the same time, but it's different tasks, right? So it's different things. So we have our data source, which is pulling vehicle events in from the IoT sensor and emitted them into the streaming job. That's one task. And then we have our other component, which was our operator, that is counting the vehicle events. That's another task. These things are both going at the same time, doing different operations, running concurrently. That's called task parallelism. Now, I've touched on parallelism. I've touched on concurrency. What's the difference? There's sometimes, you could start a war if you use this the wrong way in a tech room. Remember, and hopefully I say this right myself, parallelism is many of the same things at one time. Concurrency is many of different things at the same time. So parallelism is many of the same, concurrency is many of different, all at the same time. I think I've kind of lectured enough on using slides. Let me take a second to show you this framework that Ning built. It's absolutely fantastic. So what we did was we had a challenging moment where we were writing this Grokking book, right? So the purpose behind Grokking Streaming Systems is that you can take the book, you can read it, and then you can apply what you've read to any streaming framework that's out there today. So it's not technology specific. And to do that, we had to pull away from existing systems like Apache Heron or Apache Storm or Flink or Kafka Streams and all that, because they each have their own way of doing things. So we had to sit back and we had to really write this in a general way that maps to everything. And to do this, my co-author Ning, my friend, did a great job of writing a mini streaming framework for you all to use. And that was part of that download link I showed you earlier. I'll show you in a little bit. But let's go ahead and jump into some code and show you what it's like to run. We have 3 jobs we're going to run today. And basically, Ning wrote there's a whole bunch of code here underneath the covers that I'm not going to get into. It would take hours. He is quite the wizard of writing code. We have basically a main function that allows you to define a job. And the beautiful thing about this is that the way Ning wrote this allows you to build your own components. And, if you want to experiment with it, honestly, learning this framework isn't going to get you too far in the real world, but it's fun to play with. And he's done a really good job of building. Our first job I'm going to show you and how it behaves through terminals, because we're all back end here, right? Is the most basic vehicle counter job we talked about. That's one source. That's one IoT sensor reader, and then that's one vehicle counter. So we got 3 terminals running. Hopefully y'all can see. So what I'm doing here with this so this tool NC, all I'm doing is I'm just using a tool called Netcat to create a process that is going to basically pipe data into port 990, which is up here on the left, and then 991, which is here on the right. And these are think of these as our 2 IoT sensors, right? So these are the things going to be emitting data into the job. And then what I'm doing down here is, just to show you how to use it, you can do a Maven install or a Maven package to kind of build the project. It only takes about a second or 2. We have our first job. Hopefully it's still there. This is our vehicle count job, our original one. One of the nice things that Ning also did is he built a visualization UI where you can actually see the components that are running in the job. It's very basic. You can see that, we have one sensor reader, we have one vehicle counter. We have one sensor reader and one vehicle counter running in the jobs for you to just to understand what's going on. This first job is only going to read from my first input terminal because I only have one data source listening right now. So if I do the word car and I say, a car came across the bridge, you should see down here that and I have a little bit of a lag here, so if I get ahead, I apologize. No. So I typed the word car into my first terminal, which is emulating the sensor reading a car is going through the bridge. And then you can see down here that the sensor reader read in the event car, and then it routed it to the vehicle counter. And it counted as one car, right? And then it's got 2 cars. And then if you pipe in a truck, you got one truck. And do a van, you have a van. And, this is the most basic, simple streaming job, right? Terminals are so fun to look at while you're going through code. But as you can see, the streaming job takes the event as it hits port 990, and then pipes it into the job, which does some counting of vehicles and then prints them out to the terminal. It's as simple as that. So, that's the basic use case. So let's talk about what happens when you have 2. So in this case, we have parallelized vehicle count job 2. And let me go back over here to the code. So the first one, all you saw was we had a job. And to that job, we added a source, which we called sensor reader. This value is actually off a little bit because this is chapter 3. And then to that job, and from that source once you add a source to it, it creates a bridge stream. And then that bridge stream, you can then apply an operation to it, which we call the vehicle counter, which we have a parallelism of 1. And then we start the job and it runs. It runs in the background, or it didn't run in the background, it runs right here. And because of this, we have one vehicle counter. In this case, we have 2 sensor readers, but I was only using one for the time being. So if we get into the vehicle count job 2, we have 2 sensor readers, and I'm going to use both of them this time. And then they're starting on port 9990, and then it goes up to 9991. And then we also, from that creating the source, we return a bridge stream. And to that bridge stream, we apply an operator. And that operator is a vehicle counter. We have 2 of them. And so even though we have 2 sensor readers and 2 vehicle counters, you're only going to see 1 box regardless. And the reason for that is that's typically how it works in any streaming system. You'll have, you can have 1,000 vehicle readers, but it'll only show 1 on the UI just, because it wouldn't fit in the UI. So you have to be able to understand what you have logically. I think we started job 2 already. If I go to my sensor 1, there's a difference you see in the logout, in the logging, hopefully on the job. I'm pushing data in instance 0, and it's a car, and it's being routed to instance 0, and it's printing out car. It's counted one car. There's going to be 2 instances of a sensor reader and 2 instances of a vehicle counter. So you'll have instance 0 and instance 1. So let's do it. Let's push car in the sensor reader 1 again. And now you see, sensor reader 0. You see that another car came through instance 0 of the sensors. But then vehicle counter instance 1 picked it up this time, and it only counted a car of 1. That's okay. That's expected, right? So, and I'll get into more details of how this is done. And let's just try car one more time. And now this time you should be able to see that sensor reader instance 0 took in a car, and then vehicle counter instance 0 now has counted 2 cars that's crossed the bridge. Before we had 1. Now we got 2. Now that's the next one that came. And you can keep doing this for trucks. You can keep doing this for, you can do it for anywhere. I mean, really anywhere you want to, right? So this time, instance 1, vehicle counter instance 1 picked up 1 truck. You can do it again. And this time it hit vehicle instance 0. If you've noticed, there's a behavior that's going on here, and that's something called round-robin routing, right? So what we're doing is we're evenly distributing the load of the traffic that comes into the job to the next downstream operator. So it's like pings back and forth. And say you had 1,000 of them, you just go through the whole loop of them. You go 1, 2, 3, 4, and just evenly distribute the load across the downstream operators. And the same thing over here for sensor reader 1. If I put a track in on sensor reader 1, it's picked up by instance 1, and you'll see it's only got 1. It should have been truck, so it should have been 2. Let's see if it gets there again. We did truck this time. And this time it came over to instance 1 or instance 0, which got routed, the truck got routed to the original or the instance 0 vehicle counter, and now there's 2. I won't make you stare at these black and green screens for too long, because I know they can be very dull. But this is a scaled out streaming job, and if you notice, one of the challenges is that you have different instances of those downstream components, which are the vehicle counters that are getting data, which seemingly is at random. You as a remote API or somewhere else, you wouldn't know which vehicle counter is going to process your data. And if you code it correctly, that's not a problem. But there are use cases where you want to predictably route your data to a specific instance of a streaming job. And I'll get to that here in a minute. So how does it work, right? How does it know which one goes where, and how does it know which data pulls from which, and so forth? There were some details I left out on purpose. Well, maybe not completely on purpose, because as I was talking about, I realized I should have mentioned some of it. But there's some stuff that goes on underneath the hood that you should know about, that has to deal with routing data back and forth, and how you can predictably route it, and how you can set that routing, or that grouping, as we call it, of data to other components. So if you remember, we had the original job we had 1 reader and it had 1 vehicle counter. And then we had a second job, which we just redeployed or reran, which had 2 sensor readers right here, which were reading off each one of my terminals that I had. And then we had 2 vehicle counters. And the behavior we saw is that each vehicle counter basically pseudo-randomly got the next event in the job. And that was like that for a reason, but that's typically how streaming frameworks work for the most part. And that's called a grouping, or in this case, it's called a shuffle grouping. I'll get to it in 1 second. But one thing I didn't tell you is that it's not like data just sends a and it's not like an IoT sensor just pushes data to a vehicle counter, or like via REST, or a vehicle counter doesn't pull data from some log from an IoT sensor. What happens is and I'm talking generically here for every streaming system, is that there's these things called queues, the data structure, right? First in, first out. So as data gets put on the queue, it gets taken off by the vehicle counter. And these intermediate queues exist between each component in the streaming job. This is how this is one of the ways that we try to process events in order as much as possible. Well, here in this first job, it made sense to have just a single queue. It's easy, right? The IoT sensor reader pulls an event from the bridge, from the IoT sensor, and it puts it on a queue. And then the vehicle counter then pulls it off the queue and then counts the event and then moves on. How does that happen? But the next thing, the next question is that how does that happen when you have multiple downstream components or even upstream components? How do you reliably route that data so that you know what behavior to expect from your job? So that's where groupings come in. We have there's two of them. There's several, but the two I'm going to cover, which I think are the most widely used, are shuffle grouping and fields grouping. Let's step into shuffle grouping. So if you remember, if we step back, we had this blue queue here that was being pulled in by this vehicle counter here. And what we're doing is we're just scaling out to two vehicle counters, and we're going to need to figure out a way to get these elements to the correct vehicle counter component. And so if you look at what we had was the blue queue, which is now a white queue with cars in it, or vehicles. And you see these boxes here on the right. These are the vehicle counting components. And what shuffle grouping does is it allows for a round-robin distribution of events from an upstream queue to go to the next downstream component. So typically what happens, and this isn't the same for every streaming framework, is that there's an upstream set of components. They all place their events on the same queue. And then that queue is then picked, has then events pulled off of it and then put on another queue, which is specific to the downstream instance of where that data is going. So there's a few details missing here, and I'll get to it, but the overall gist you need to get, or I want you to understand, is that it's round robin. Truck goes vehicle counter 1, van goes vehicle counter 0, car goes 1, truck goes 0. It doesn't matter what the event is, it just goes back and forth. So how does it work? Let's get into a little bit of math here. It's simple math, but grouping data it can be a misleading word for because you think of it's being routed, right? I think routing is a little bit different than grouping because in this instance we're talking about parallelization, right? We're scaling out the same operation in a component many times. And we're not necessarily routing our data to a new component. That would be another operation. What we're doing is we're grouping data reliably to each specific instance of the component so that we can properly parallelize this job out and process data faster. And what shuffle grouping does is probably the most simplest. It just goes back and forth, right? It starts at instance number 0, pushes data to it, adds 1 to instance number. To the instance number, just adds 1 to it, and then it goes to the next. Once it hits the top of the top number, it goes back to 0 and resets, and then it just kind of keeps going back through. And that would work if it had 2 instances or if it had 1,000. And you'll also see some wording here about an operator instance executor. That's actually covered in a little bit more detail in chapter 2 of the book. That's one of the things that runs the actual instances of the components that you build. But if you check it out in chapter 2, it can walk you through it in a little more detail. So then there's fields grouping. What's the difference? Fields grouping allows you to predictably route data to a specific downstream instance component. So right now we have toll booth 1, toll booth 2. They should be 0 and 1, but typo by me. The way fields grouping work is that vans, in this case, vans always go to toll booth 1. You can see it here, and you can see it here and here. These last 2 vans, they all go to the toll booth 1. And then you can also see that a car is also routed to toll booth 1. If there was another car in this queue, it would also be routed to toll booth 1. And then trucks are always routed to toll booth 2. Why? I'll get into it. Hashing. So fields is called fields because you hash a field in a data element that's going through a job. An element, I may use the word tuple from time to time. An event that goes through a streaming job, or an element that goes through a streaming job, or a tuple that goes through a streaming job are all the same things. So if I missed that earlier on, I apologize. But fields grouping is you take a field out of the object or the tuple that's being passed into the streaming job, and you create a hash on it. And you calculate some big large number, you divide it by the hash of the value, and you reliably get the same downstream instance number every time. And the way this field grouping works is something here called a key space. Your key will be, it's at a very high level. You take some big large number like 98,632. You modulo it and then you multiply it by the value of the hash of the field that you select, and then you modulo it by the number of downstream instance executors you have, and then you get some lower number. So in this case, say we have 2 instance executors, you would modulo, or you would take the hash of whatever the value is of car or van, and then you would modulo that by which is some usually large number. And then you modulo it by 2, and then you get whatever's left over. And either it's 0 or 1. And that'll tell you where to route the downstream data. How do events know to go from one queue to the next, right? Because I talked about there's a single queue for the most part that all of the upstream components put data on, at least in our case. And so those upstream components, just to refresh, would be the sensor readers, right? So they're all reading data from the IoT sensor bridge and the IoT bridge sensor, and they're putting them on this queue you see here on the left. And then the grouping logic execution is then performed in between the movement of these queues, right? So there's a process that runs in between both of these sets of intermediate queues that decides where the data goes. And I'll get into a little bit of the name of it. It's called a stream manager, but basically it's a constantly running process that pulls new data off the queue on the left. It performs the grouping logic, which we said would either be shuffle or fields at this point, and then puts it on the corresponding downstream output queue, which would be the queues on the right. Okay, Stream Manager is specific to, I have to be honest, Stream Manager is specific to Apache Storm and Apache Heron. That's a fault of mine. In the book, we use the term event dispatcher. We tried to keep it as generic as we could for the book. One of the things we didn't want to, as we were writing this, as we were writing Grokking Streaming Systems, we didn't want to bake one person into one technology, because if they took all that time to learn it and say the technology went out of date, well, their skills may not be they may not be as happy with the purpose of the book. So we built this in the most framework agnostic way, and the code that we wrote you, or actually Ning wrote you, we titled Streamwork, and this is what we named it. So this is, if we get into the details of the code and you step back through chapter 1 and chapter 2, you would be a little bit more prepared to look at this diagram, because there's a lot of stuff going on here, right? So if you look at the top, we have this familiar diagram that we've seen. It's the DAG, right? It's the 2 IoT sensor readers, and it's the 2 vehicle counters, and they're pushing data to each one. If you zoom down another level, you're going to have something called a source executor, which is the bigger boxes, and you're going to have an operator executor. That's the bigger box on the right. And then for each instance of each type of component, there'll be that instance executor, and then there'll actually be the component code that is being ran by the executor. So each one kind of runs itself. And now this isn't true for every streaming framework. This is just the way we built this. Ning built this. He did a great job, I got to say. We were writing this, and we were trying to plan on how to do this, and I think he cranked this code out in like 2 weeks. It was just amazing, and it's really good to learn from, and it's really good to apply concepts that you get from this to real frameworks. But so I guess to go back on track is you have this event dispatcher, right? So you have two downstream components, which would be your sensor reader, instance 0, and sensor reader, instance 1, both pushing data into the event dispatcher. And in this case, for simple purposes, we'll say that there's one queue it's pushing data into. And then the event dispatcher has some code that's actually separating that single input queue into two output queues in this case, because we have two downstream instances. If we had 1,000 downstream instances, it would separate into 1,000 queues. So just to kind of refresh here, and hopefully I didn't go off the deep end here. We have downstream components are putting all their data on one queue. And then your stream manager, or your event dispatcher, is pulling the events in order off of that queue and then placing them based on the grouping logic execution onto the next downstream queue. And that could be any one of those instances. It could be 1 or it could be 1,000. This is a continuously running job, which creates a stream. The coolest thing is that if you really boil down technology, it all boils down to the same concept, really. So if you ever wondered what a stream really is, it's just a continuous movement from one data structure to another. That's it. That's all the stream is. It's just one to the next. And that's it. And that's what creates the concept, or that's what creates the stream. It's just a continuous movement.